Consider the differential equation given. A. Use Euler's method with h is 0.25 to find an approximate value of y when x is 1, giving your answer to 2 decimal places. So, according to the Euler's method, the next y value is the current y value plus a step multiplied by the derivative at the current point, and this formula is given in the data booklet. And for the calculator, let u be y, v be x, and for the calculator n-1 it means the current point, and n it means the next point. So the next y value, it becomes u of n is the current y value to u of n-1 plus a step here 0.25 multiplied by derivative, and derivative we just solve given differential equation for dy over dx, and you can see it's 1 minus xy over 4 minus x squared. But you must write of n-1 all time for x, for y. So you can see it becomes 1 minus x, which is v of n-1 multiplied by y, which is u of n-1 divided by 4 minus v of n-1 squared. And since the initial point is x is 0, y is 1, so the initial y value is 1, so u mean is 1. V of n, it's the next x value, it's the current x value plus a step, so v of n is v of n minus 1 plus 0.25, and the initial x value is 0. So using a calculator, and first of all you choose mode, and you should choose sequence, not function but sequence, then y, and you can see that u of n is u of n minus 1 plus 0.25 multiplied by 1 minus v of n minus 1 multiplied by u of n minus 1 divided by 4 minus v of n minus 1 squared, and u mean is 1, v of n is v of n minus 1 plus 0.25, and v mean is 0, and then you just choose table, and v is x, u is y, and we need y when x is 1, so you just choose v to be 1, and you can see that u, and it's the required y, is 1.84 to 2 decimal places as required. Y is 1.84. And the next, by first finding an integrating factor, solve the differential equation, give your answer in the form y is f of x. It is given that you should use an integrating factor method, but you should understand that if an equation and when the differential equation looks like a derivative plus something of x y is equal to something of x, such differential equation can be solved using a method which is called by integrating factor. And notice that if there is something in front of dy over dx, you must divide each term by this to get just dy over dx without something in front. And then the next step is to find an integrating factor. Formula is given in a data booklet, and it says that the integrating factor is e to the power integral p of x, and p of x it's an expression in front of y, so it's x over 4 minus x squared dx. And how to integrate this? We can use substitution u, and u to be the denominator 4 minus x squared. Then du over dx, it's what? It's negative 2x, and dx is du over negative 2x, and then we get e to the power of integral x dx is du over negative 2x, and you can see x cancels, and 4 minus x squared is just u, and we get e to the power of negative a half integral du over u, and du over u it's a ln of u, and u is 4 minus x squared. In general, it's a ln of the absolute value, but this absolute value is not required for integrating factor, and also it is given that the absolute value of x is less than 2, so 4 minus x squared is positive. So it becomes e to the power of negative a half ln of 4 minus x squared. And to simplify it, we use the next property that a to the power of log a log to the base a of b is just b, and if there is something in front of log, for example 2, we move it to the power of b using another property of log, and finally it becomes b squared. And here it becomes what? E to the power ln 4 minus x squared to the power of negative a half, and it becomes just 4 minus x squared to the power of negative a half. It can be written as 1 over root over 4 minus x squared. And the next step is we multiply each term by this integrated factor, and notice that you must write this step. You may write 2 a power negative a half or 1 over root, it doesn't matter. So it becomes 4 minus x squared to the power of negative a half dy over dx plus what 4 minus x squared to negative a half xy over 4 minus x squared, and is equal to 4 minus x squared. Or let's rewrite it as a root 1 over root 4 minus x squared. And it always be true that the left hand side it becomes d over dy. It's d over dx. It's a derivative with respect to x of the next expression. It's integrating factor. Or let's rewrite as a root 1 over root 4 minus x squared and multiplied by y. It's always true. And is equal to this 1 over root 4 minus x squared. So it looks like derivative of something is equal to something. And how to find function if you know derivative? You need just this function is equal to integral of this. Or as a differential equation, you may integrate both sides, and integral of derivative is just a function. So it becomes 4 over root is equal to what? Integral of this dx. And to integrate this, formula is given in a data booklet, and it says that 1 over root a squared minus x squared dx is arcsine x over a plus a constant. And notice that 4 is 2 squared, so a is 2, no, not 4. So it becomes integral, and integral is arc sine of x over 2 plus a constant. And let's find a constant. To find the constant we need a point, and point is the same 0, 1. So substituting 0, 1, we get 1 over root 4, it's 2, is arcsine of 0 is 0 plus c, so the constant is a half. And we need the answer to be in the form y is, so we just solve for y, and it becomes root 4 minus x squared multiplied by arcsine of x over 2 plus a half. And we need the same, no, not the same, the value of y at the same x value, but using this exact solution, so we will get the exact value, and we need again when x is 1. So substituting x is 1, we get that y is, you can see that it's root 3 multiplied by arc sine over half plus a half. And using a calculator, so now we choose again mode, and there must be radians. It's very important, not degrees. Radians, and again functions, and just it becomes square root of 3 multiplied by arc sine over half plus a half. And we get y is 1.77, y is 1.77 to 2 decimal places, and you can see that our approximated value is larger, so it's called overestimated. It's larger, so it's overestimated. And the next question: sketch the graph y is f of x for x is from 0 to 1. Use your sketch to explain why your approximate value y is greater than the true value. You may just use your calculator. I just write the required graph. So from when x is 0 it's 1, when x is 1 it's 1.77, so 2 is to be more correct, 1, 2, so it's something like this, and let it be 1, 1, so it's 2, and it's 1.77, but it's not required. It's important to understand that this curve is concave down and increasing, and let's consider when we get overestimated, when underestimated value. And for given curve, it's our endpoint, it's the next point, and we draw a tangent at endpoint and point xn. And how this formula works: the next y value is the current y value plus derivative dy over dx at and multiplied by h, and derivative at the current point. But we know that derivative it's what? It's derivative at the point, it's gradient over tangent, and gradient over tangent or gradient over line is equal to tangent of this angle between positive direction, it means direction to the right of x-axis, and a given line. So this is equal to derivative at the point, so it's derivative at xn, and also it is given to tangent of theta. And what is tangent? It's rise over run, or it's delta y over delta x, and delta x it's actually our step, which is h, and it's the next point x plus 1, so it's y n, and you can see that it becomes the next y value, it's the current y value, this plus h multiplied by the derivative, but derivative it's delta y over h cancels, and it becomes, this becomes delta delta y, so this is y approximate, but you can see that it's true value, or exact value, it's y exact or true value, and hence you can see that our estimated value is great, it's called overestimated. If curve would be increasing and concave up, hence you can see that this value, it will be approximate, will be calculated value, and it's true value, exact, and in such situation it will be underestimated value. And actually you may explain using such a sketch. So since curve is increasing and concave down, concave down, approximate value is greater than the exact value. So approximated value is overestimated. And also we can add the next and write the next, that method suggests that derivative dy over dx is constant throughout each interval. It means this. You can see that it is suggested that from this point to this point, since tangent is a straight line, so it is suggested that tangent of the curve is the same and is equal to tangent of the tangential line. But gradient of the curve changes continuously, and since a curve is increasing and concave down, gradient of the curve decreases continuously, but tangent method, I actually rewrite the same but with respect to a given curve, but method suggests a constant gradient throughout each interval. Therefore, approximated value is overestimated. So over or underestimated, it depends on the curve to be concave up or concave down, or increasing and decreasing, and you may conclude just using such a sketch. And there may be a question just state over or under, so you need just give the answer. And to explain, you may give a sketch, for example, maybe appropriate method, but again, how to explain? So if it's for example increasing and concave up curve, so it implies what? The curve or gradient of this curve is increasing continuously, but method suggests that you can see that gradient is constant within each interval, and that's why the calculated value is less than the actual value. And if curve is increasing but concave down, you can see that the gradient of the curve decreases continuously, but method suggests gradient is constant throughout each interval, hence calculated value is greater than the actual value, so we will get overestimated value. And that's all for this question.